In this section, we're going to begin by introducing the idea of an exponential function. I'm going to start with the definition. So an exponential function is essentially one that has the x in the exponent. All right, so that's the easiest way to recognize an exponential function is to look for your x, and if your variable is in the exponent, then you're looking at an exponential function. Now the a part of this function is going to be substituted in with a number when we're looking at actual examples. That number is referred to as the base, right? So that's important to know that the a is referred to as the base of the exponential function. Now that base is a number that has to be greater than 0, so it has to be a positive number, and the only stipulation is that it can't equal 1. All right, so we want to take a second and talk about the graph of an exponential function. Now, the graph of an exponential function, most of the graphs for exponential functions look very similar to the graph that you see on the screen. So this is the graph for f of x is equal to 2 to the x. If I were to change it and do f of x is equal to 3 to the x, the graph would look very similar. If I were to, on my calculator, graph the graph of f of x is equal to 4 to the x, then I would have the same type graph. So it's interesting to note that regardless of what your base is, as long as that is bigger than 1, then you're going to have a graph that looks like the graph on the left-hand side of the screen. All right, so I'm going to make that note here. So as long as, we'll just say for all a values that are greater than 1, then our graph is going to look like this. All right, so the next thing that we need to be thinking about then is what happens in the case if our base value is not greater than 1. Now remember, we are forced to have the a value be positive. So if I'm talking about numbers that are less than 1 but are still positive, I don't have many to look at. So if we have that happen, where the graph basically flips around, mirrors over the y-axis, and it has the same shape. So this is going to be the graph for any a value that falls between 0 and 1. And remember that the a cannot equal 1, and it has to be positive. So this is sort of all that's left is those fraction values between 0 and 1. So this would be the graph of something like, for example, f of x is equal to 1/2 raised to the x power. All right, and so that simplifies things a little bit to realize that the graph is either going to look like this for a values that are bigger than 1, or it's going to look like this for a values that are between 0 and 1. So those are our two options, and those are our two graphs for exponential functions. All right, so in terms of what we need to be able to work in this particular section, one thing that we need to be able to do is we need to be able to evaluate an exponential function. Now this is fairly easy because we do have our calculator to help us with this. So let's just look at a quick couple of examples. The first one, f of x is equal to 2 to the x, is our function, and we want to find f of 6. So remember that when you're evaluating a function, that you're going to take whatever's in the parentheses and you're going to plug it in for x. And so we would come to our function, and in place of this x, we would put a 6. And so evaluating f of 6, we would have 2 to the 6th power. And then we would go to our calculator with that. Now when you enter it in, most of you have a calculator similar to the one that I have on the right-hand side. So you should be looking for a button that looks like that caret button to use for your powers. So you can try that, and if you have any trouble with your calculator and you aren't able to get the answer of 64, just let me know, and I can help you with your calculator. All right, so let's try one more. What if we had a function f of x is equal to 3/2, and we're raising that to the x? Now, the process stays the same. Whatever we have inside the parenthesis, we're going to plug in for the x. So we're going to be substituting in a -4 for that x value. And so rewriting that problem, we'll have 3/2 raised to the -4 power that we want to evaluate. And not only do we want to evaluate it, but we want to give our final answer in terms of a fraction. So again, we can do this by hand, but we do have the calculator with us, and so it's probably easiest to type it in the calculator. So notice on the first picture here, I have it entered in. Be sure that you put the 3/2 in a set of parentheses, and then you're going to use the caret key, wherever that may be on your particular calculator, to raise it to the -4th power. And you can check your decimal and make sure that you have entered that part correctly. Once you get that correct decimal, you then need to convert it back to a fraction. So you are looking on your calculator for the F arrow D button, which for me is above my PRB button. So I'm going to need to use the second key and then this PRB button to convert that back to a fraction. So if I press that key sequence and then press enter, it should give me a final answer of 16/81. And again, if you find that you're having trouble with your calculator, you can either let me know the next time that you're in class, or you can shoot me an email and ask questions. All right, we do have a special case that we look at when we talk about exponential functions. And this special case is the exponential function that has a base e. Now, you may remember working with the e in another class. The e is kind of like pi in that it's an irrational number that has this decimal that goes on forever. So e is essentially 2.71828, and then that decimal continues. And so remember that our typical exponential function that we gave at the beginning of the presentation looks like this. Okay, remember that this is your base, the a. So now all we're saying is that we're putting in a specific base. So instead of the a, we're going to put in this e approximation, and this is going to be an exponential function. All right, and so you can see that at the second bullet point, we have f of x is equal to e to the x. And we use that special case, that e, in applications, which we'll see in just a couple of minutes. All right, so just a couple of quick problems with it. The first one, let's evaluate. It says find f of 1.2 for f of x is equal to e to the x. Remember, whatever is in the parentheses, in this case 1.2, is going to go in for the x. So we're going to be evaluating e to the 1.2. Now, you do have this button on your calculator, and I didn't do a screenshot here, but I'm hoping that you can look and find it and be able to enter that in. And so if you do that, you should get, and we're going to keep these as decimals, I'm going to round to 2 decimal places, 3.32. And again, if you have trouble finding that button on your calculator, just let me know. All right, so what does the graph of the function e to the x look like? All right, so what I'm asking you here is, when I draw the graph of that function, is it going to look like that situation or this situation? Okay, so remember that the graph that you have depends on your base. You're using this graph if your base is bigger than 1, your a value, and you're using this graph if your a value is between 0 and 1. All right, so our base value is bigger than 1. It's 2.7 approximately. So if the a value is bigger than 1, the graph should have that shape to it, starting at the left and working its way up into the first quadrant. All right, so right here, you should be able to determine that the graph is essentially going to look like this. And we just want a rough sketch here to determine which way that graph is going to turn. Okay, so as I said, the E, that special case E, is typically used in applications. So I want us to look at two word problems and look at how this E base is used in an exponential function. So we typically see this with examples of exponential growth and decay. And all exponential growth and decay problems are going to be based on a formula that looks like this. A is equal to P times E to the RT power. All right, so when we have that formula, what you want to keep in mind is that the A is going to be your final value. We'll try to make some notes here. This is your final value. The P is going to be your initial value, so whatever you start with. All right, the R is going to be your rate of either exponential growth or decay, and T is going to be your time. So those two hopefully are fairly straightforward. So I'm just going to make a note here. R is the rate of growth or decay, and T is the time. So for the most part, these problems are fairly straightforward in that we're going to simply be plugging numbers in the correct place. All right, so let's look at this example. A motorcycle bought for $10,000 depreciates continuously at 9%, and that phrase means per year. What is its value after 7 years? Round the answer to the nearest dollar. All right, so as I look at my formula, I know that the initial value of the motorcycle was $10,000. So that initial value is going to go in for the P. I know that the motorcycle is depreciating at a rate of 9% per year. So that's going to be my rate. Now that rate does need to be written as a decimal. So I'm going to write it as 0.09. It also needs to be a negative, and it needs to be a negative because it's depreciating. So if we're talking about decay, our rate should be going down. If we're talking about growth, our rate should be positive and going up. Right? And then the time that we're looking at is 7 years. So I'm going to put a 7 in for the T. And then all I need to do is go to my calculator and type that in using the E button on your calculator. So we would put the 10,000 in first. We would press our E key, and if it gives you the exponent, then you're ready to go. If it doesn't, you would need to use your caret key. And then be sure that you put your exponent in a set of parentheses. So 0.09, negative 0.09. times 7. All right, so you can try that, and we will get, let's see what we get here. All right, so I get 5325. .91801, and it does say to round to the nearest dollar. So we're going to be looking at 5326 for the value of that motorcycle. All right, let's try one more. A radioactive substance has a continuous decay rate of 0.056 per minute. How many grams of a 120 gram sample will remain radioactive after 40 minutes? Round the answer to the nearest tenth of a gram and do not include the unit in your answer. Now this problem I pulled straight from Newton, so you will have similar problems to this as you're working on your homework. All right, so again, we're going to take that formula, final value equals initial value times E raised to the R times T. And we know that our initial value, what we started with, was 120 grams, so that's going to go in for the P. I know that my rate that it's decaying at is 0.056, so that's going to go in for the R. And again, it is a decay rate, so it's going to be negative. And our time is 40 minutes. And so I'll put a 40 in for the T. All right, and again, at that point, it's just a matter of putting it in your calculator. And so when I type that in, I'm going to get 12.775 for my answer. And it says to round to the nearest tenth of a gram. So I'm going to be looking at 12.8. So again, the application problems should stay pretty basic. The main thing to remember is that if you're dealing with a decay problem, you want to put a negative on your rate. If you're dealing with a growth problem, you want to leave it positive. And as I said, if you have any trouble entering these into your calculator and getting the correct answer, just let me know.